Hi, it's Sleepy Steve helping you to fall asleep and study. Remember to subscribe to help Steve-O out, and I will keep making more sleepy stories. Tonight, we are staying in Unit 3 Physical Education, Area of Study 1, and we are moving from practice and feedback into the quiet science of movement itself. In the last episode, we looked at how movement skills can be improved through different types of practice and different types of feedback. Now we are going to look at what happens inside the movement. How does a performer create force? How does a ball travel through the air? Why does a wider stance make someone harder to push over? Why does a good kick, throw, shot, jump, or serve often begin in the legs, travel through the body, and finish through the smallest parts of the movement? These questions belong to biomechanics. Biomechanics is the study of the mechanical principles that explain how the body moves. It helps us analyze movement skills, improve technique, increase efficiency, produce more power, improve accuracy, and reduce the risk of injury. You might picture a quiet school oval in the late afternoon. The grass is soft underfoot. The sun is low behind the trees. A football rests near the boundary line. A basketball sits quietly beside the court. A student is preparing to sprint. Another is preparing to jump. And another is simply standing still, balanced and calm. Nothing is rushed tonight. Every movement is slowed down, almost like a gentle replay. And as we watch each movement carefully, the hidden principles of biomechanics begin to appear. Let's begin with force. A force is a push or a pull that can change the motion of an object or body. When a sprinter pushes down and backward into the track pushes back up and forward into the sprinter. That ground reaction force helps the sprinter accelerate forward. When a footballer swings the leg and contacts the ball, the foot applies force to the ball, and the ball changes from resting quietly on the grass to moving through the air. When a basketballer jumps for a rebound, the legs apply force into the ground, and the body rises upward. In physical education, it is useful to remember that force is not only about strength. Force also has direction, timing, and purpose. A large force applied in the wrong direction may not improve performance. A smaller force applied at the right time, in the right direction, can sometimes be much more effective. So when we analyze movement, we do not just ask how much force was produced. We ask where the force was applied, when it was applied, and how it affected the movement. Now let the football rest still in the grass for a moment. It does not move by itself. It stays where it is, quiet and still, until something acts on it. This introduces inertia. Inertia is the tendency of an object or body to resist a change in its state of motion. An object at rest tends to stay at rest. An object moving tends to keep moving in the same direction and at the same speed, unless acted on by another force. A ball will not begin moving without a force. A runner will not accelerate from a standing start without applying force into the ground. A performer changing direction must overcome the inertia of their own body. This is why rapid changes of direction in sport require strength, control, and good technique. The body must slow down, control momentum, and then apply force in a new direction. Now the student steps forward and gently kicks the ball. The ball begins to move. Its velocity changes. That change in velocity is acceleration. Acceleration is the rate at which velocity changes over time. In performance, acceleration might mean speeding up, slowing down, or changing direction. A sprinter accelerates from the blocks. A netballer decelerates before landing and passing. A tennis player accelerates the racket toward the ball. A footballer changes direction to evade an opponent. A useful exam explanation might say that increasing the force applied to the ground during a sprint start can increase acceleration because the performer creates a greater ground reaction force in the opposite direction. The key is to link the biomechanical term to the movement outcome. Not just force, but force leading to acceleration. Not just inertia, but inertia being overcome when the performer starts, stops, or changes direction. Now we watch a runner move across the oval. At first, the steps are light and gentle. Then the runner increases speed. A moving body has momentum. Momentum is the quantity of motion a body has, and it depends on mass and velocity. A faster performer has more momentum than the same performer moving slowly. A heavier object moving at the same speed has more momentum than a lighter object. In sport, momentum matters because performers often need to create it, transfer it, use it, control it, or reduce it. A rugby player carrying the ball at speed has momentum. A long jumper builds momentum during the run-up before takeoff. A tennis player creates momentum through the body and racket during a serve. A gymnast landing from a jump must absorb and reduce momentum safely. Momentum is not always something we want to maximize. Sometimes we want more momentum to improve distance, speed, or power. Sometimes we want to control momentum to maintain balance, land safely, or change direction efficiently. This leads us to impulse. Impulse is the application of force over a period of time, and it produces a change in momentum. In simple terms, impulse depends on force and time. If a performer can apply a force for longer or apply a greater force, they may create a greater change in momentum. Imagine a jumper bending the knees before takeoff, then extending through the ankles, knees, and hips. The performer is applying force into the ground over time. A strong, well-timed push can help increase upward momentum. Now imagine catching a fast ball. If the hands are stiff, the ball stops very quickly, and the force on the hands can feel high. But if the performer gives with the ball, moving the hands backward as the ball is caught, the stopping time increases. The change in momentum occurs over a longer time, so the impact force is reduced. This is why performers bend their knees when landing, draw the hands back when catching, or roll after a fall. They are increasing the time over which momentum changes, which helps reduce force and protect the body. In an exam answer, this is a strong connection. A gymnast bending the knees on landing increases the time over which momentum is reduced, lowering the force experienced by the body and reducing injury risk. Now the oval becomes a basketball court for a moment. A student stands at the free throw line. They bend the knees slightly. The legs extend. The hips and trunk rise. The shoulder lifts. The elbow extends. The wrist flicks softly, and the ball leaves the fingertips. This movement is not just an arm action. It is a sequence. This is summation of momentum. Summation of momentum occurs when momentum is transferred through body segments to produce an efficient and powerful movement. Usually, larger and stronger body parts begin the movement, and smaller, faster body parts finish it. The movement flows from the larger segments to the smaller segments, like a quiet wave moving through the body. In a tennis serve, force begins through the legs, then moves through the hips, trunk, shoulder, elbow, wrist, and racket. In a golf swing, momentum is built through the legs and hips, then transferred through the trunk, arms, and club. In a football kick, the approach and support leg help set up the movement, the hip and thigh begin the action, the lower leg swings through, and the foot contacts the ball. If the sequence is well timed, the final segment can move quickly, and the outcome can be more powerful and accurate. If the timing is poor, some momentum may be lost. The movement may feel awkward, less powerful, or less controlled. A useful phrase for VCE physical education is that effective summation of momentum requires correct sequencing, appropriate timing, and transfer of momentum from larger body segments to smaller body segments. It is not enough to say the performer uses the whole body. The stronger answer explains how the movement flows and why that improves performance. Now we return to the football resting near the boundary. The student takes a gentle run-up and kicks the ball into the evening air. The ball rises, travels forward, slows at the top of its path, and then falls back toward the grass. This is projectile motion. A projectile is an object that is released into the air and then moves under the influence of gravity and other forces such as air resistance. In sport, many objects and bodies become projectiles. A basketball after a shot, a netball after a pass, a football after a kick, a javelin after release, a long jumper after takeoff, a diver moving through the air before entering the water. The path of a projectile is influenced by speed of release, angle of release, and height of release. Speed of release is how fast the object or body is moving at the moment it leaves contact. A greater speed of release can increase the distance traveled if the direction and technique are appropriate. Angle of release is the angle at which the projectile leaves the body or equipment. A higher angle may create more height. A lower angle may create more horizontal distance or speed. Height of release is the height of the object or body at the moment it is released. In many sporting movements, the ideal angle is not always 45 degrees. That is a common starting idea, but real sport is more complex. A basketball shot is released above the ground and must enter a hoop higher than the release point. A javelin is affected by air resistance and the design of the implement. A long jumper takes off from the ground, but must balance vertical lift with horizontal speed, so a strong answer does not simply memorize one angle. It explains that the optimal angle depends on the activity, the height of release, the desired outcome, and the performer's technique. Now, let the football settle again, and let us look at the body as a system of levers. A lever is a rigid structure that rotates around an axis when force is applied. In the human body, bones act as levers, joints act as axes, muscles provide the force, and body weight or external objects provide the resistance. When you bend the elbow during a biceps curl, the forearm acts as the lever, the elbow joint is the axis, the biceps provide force, and the weight in the hand acts as resistance. When you rise onto your toes, the foot acts as a lever, the ball of the foot acts as the axis, the calf muscles apply force, and the body weight provides resistance. When a footballer kicks, the leg acts as a lever system rotating around the hip and knee, helping the foot move quickly toward the ball. Levers can be used to produce force, speed, or range of motion. Some lever arrangements are better for strength, others are better for speed and movement distance. In many sporting skills, the body uses levers to increase the speed of the endpoint. For example, the hand, foot, racket, or bat may move quickly because the body segments rotate in sequence. This links back to summation of momentum. The lever system does not work alone. It works with force, timing, body position, and coordination. Now the oval becomes very still. A student stands on one leg near the center circle. At first, the arms move slightly, searching for balance. The body makes small adjustments. The ankle shifts. The hips settle. The eyes focus on a quiet point in the distance. Balance is the ability to maintain control of the body's position, whether still or moving. Static balance occurs when the body is held in a stable position, such as a gymnast holding a pose. Dynamic balance occurs when control is maintained while moving, such as a surfer riding a wave, a basketballer changing direction, or a footballer kicking while running. Stability is the ability to resist disruption to balance. A more stable performer is harder to move off balance. Several factors affect stability. A wider base of support usually increases stability. A lower center of gravity usually increases stability. A line of gravity that falls within the base of support helps maintain balance. Greater mass can increase stability. Greater friction between the body and the surface can also help prevent slipping. Picture a defender preparing to hold position. They bend the knees, lower the hips, and widen the feet. Their center of gravity lowers, their base of support increases, and they become harder to move. Picture a gymnast landing from a jump. If the feet are too close together and the body is upright and stiff, balance may be harder to control. If the performer lands with knees bent, feet apart, and the line of gravity within the base of support, stability improves. Again, the important thing is the link. Do not simply list factors affecting stability. Explain how the change in body position helps the performer maintain balance or resist an external force. Now, let us bring the ideas together through movement efficiency. Efficient movement uses energy, force, and body position effectively to achieve the desired outcome with minimal waste. Efficient movement is not always the biggest movement. It is the movement that suits the task. A runner with efficient technique may use less energy at a given speed. A swimmer with efficient stroke mechanics may move through the water with less resistance. A tennis player with effective summation of momentum may generate racket speed without forcing the arm alone. A basketballer with good balance and timing may shoot more accurately and consistently. Biomechanics helps explain why these improvements occur. It can show whether force is being applied in the right direction. It can show whether momentum is being transferred smoothly. It can show whether a projectile has the right release conditions. It can show whether body position supports stability. It can show whether a lever system is being used effectively. A coach, teacher, or performer might use video analysis to slow the movement down. They might observe joint angles, body position, sequencing, landing technique, balance, speed of release, or follow-through. They might compare one attempt with another. They might identify one small change that makes the movement safer, smoother, or more effective. This connects biomechanics to the previous episode on feedback. A performer can use biomechanical information as knowledge of performance. For example, a coach might say that a jumper needs to bend the knees more on landing to increase the time over which momentum is absorbed. Or a coach might say that a tennis player is losing power because the arm is moving too early before the legs and trunk have transferred momentum. Or a coach might say that a basketball shot is falling short because the speed of release is too low, or the summation from legs to wrist is incomplete. In each case, biomechanics gives meaning to the feedback. It tells the performer not just what happened, but why it happened. For VCE physical education, this is especially important. When you write about biomechanics, try to be specific. Name the principle. Describe the movement. Explain the effect on performance. For example, instead of saying the performer needs more force, you might say that the sprinter can improve acceleration by applying a greater backward and downward force into the ground, creating a greater forward ground reaction force. Instead of saying the performer needs better balance, you might say that widening the base of support and lowering the center of gravity improves stability by making it harder for the line of gravity to fall outside the base of support. Instead of saying the throw needs more power, you might say that effective summation of momentum transfers momentum from the legs and trunk through the shoulder, elbow, and wrist, increasing speed at release. These links make the answer stronger because they show understanding, not just memory. Now the evening on the oval is fading. The runner slows to a walk. The basketball rolls softly to the edge of the court. The football sits still again in the grass. And the movements we watched become calm little lessons. Force begins motion or changes it. Inertia resists change in motion. Acceleration is a change in velocity. Momentum builds when mass and velocity combine. Impulse changes momentum through force applied over time. Summation of momentum transfers movement through the body in a timed sequence. Projectile motion explains the path of a ball, body, or object through the air. Levers help the body create movement around joints. Balance and stability help performers control body position. And movement efficiency helps performance become smoother, safer, and more effective. That is biomechanics, the quiet science beneath every kick, throw, jump, sprint, landing, serve, swing, and shot. So as you rest now, let the concepts settle gently. You do not need to chase them. Just let them sit like equipment packed neatly beside the oval. Force, momentum, impulse, projection, balance, stability, efficiency. Each one is part of movement. Each one gives us a way to analyze performance, and each one helps us understand how the body can move with more control, more confidence, and more ease. Sleep well.